Today, I will present a scoping review paper published at CHI 2026 exploring gaze in speech in multimodal human-computer interaction. Since the 1980s, we have known that multimodal interaction is powerful because it mimics how humans naturally communicate. We don't just talk, we point while we talk, we look while we talk. A well-known example is Bowles' put that there work, where speech plus pointing resolved what that and there means together. Since Bowles' work, the capability of gaze and speech have rapidly evolved. These are now mature, accessible, and increasingly embedded in consumer devices. Gaze is fast, continuous, and low effort. You look at things effortlessly. It's a window into attention, but gaze alone has problems. It's imprecise, and critically, there is the Midas touch problem, according to which your eyes are always looking somewhere. So how does a system know when you actually mean something versus just scanning the room? Speech, on the other hand, is rich and expressive. You can convey commands, data, and meaning. But speech also lacks spatial precision. When you say move that over there, the system has no idea what that or there refers to. If we observe, we can see that gaze and speech weaknesses are each other's strength. Gaze grounds speech spatially. It tells the system what you are referring to. Speech clarifies gaze semantically. It tells the system what you want to do. Together they form a hands-free complementary pairing that's more powerful than alone. So we conducted a scoping review of 103 studies published between 1991 and 2025 following PRISMA guidelines. Our central question is, how is the combination of gaze and speech used for interaction? While prior surveys have covered multimodal interaction broadly, none have synthesized this specific pairing, and many of the core challenges like temporal alignment and fusion only emerge when the two are considered together. Our work is the first comprehensive synthesis focused specifically on the pairing of gaze and speech. We framed our synthesis according to the commonly observed form of interaction, explicit gaze and speech interaction, and implicit gaze and speech interaction. For each, we examined how gaze and speech are combined and where across tasks and domains this combination is applied. In explicit interaction, users deliberately coordinate their gaze and speech. You look at something on purpose and you say a command on purpose. It's direct manipulation, intentional, controlled, and precise. To understand this space, we identified the functional rules of each modality. Gaze serves two rules: pointing, which relates to referencing a target by looking at it, and confirmation, which uses mechanisms like dwell to signal intentional selection. Speech also has two rules: command, which refers to issuing actions like delete or zoom, and data that provides content like dictating text into a field. From these function rules, we identified three recurring combination patterns. First is gaze to point and speech as command. This is the most common pattern. You look at a target and simultaneously say what you want to do. For example, gaze a file and say open. This uses parallel integration where both modalities are processed in the same time window. The second is gaze to point plus confirm and speech as command. Here gaze first selects the target, typically through a dwell, and then you issue the speech command. The key difference is that you don't need to keep looking at the target while speaking. This is sequential integration, and it's more reliable because the system locks onto the target before interpreting speech. Third is gaze to point plus confirm and speech as data. Similar to the second, but instead of a command, the speech provides content like dictating a phone number into a gaze-selected text field. These patterns are applied across several task categories, that is selection, system control, navigation and manipulation, and language input and editing. For example, for the task of object manipulation, gaze specifies the destination and speech triggers the movement. Interestingly, while gaze speech manipulation is slower than touch, users report it as more immersive and engaging. Next is the implicit interaction paradigm, which is fundamentally different from explicit. Here, users don't deliberately coordinate their gaze and speech. Instead, systems passively observe natural behavior and infer meaning from those patterns. This shifts the design challenge from direct control to inference. The system must extract features, model their relationship, and generate predictions about user state or intent. We found that implicit systems follow a two-stage pipeline. Stage 1 is representation, where system transform raw signals into a structured feature in two ways. Independent feature extraction, which treats gaze and speech as separate channel. From gaze, different features like fixation count, saccade velocity, saccade pattern are extracted. From speech, acoustic features like pitch and rhythm, and linguistic features like keyword and semantics are extracted. Another approach is joint feature extraction, which analyzes gaze and speech together. Common features are similarity-based features that compare what the user is saying with what they're looking at, and reference-informed features which uses speech events like this as a temporal anchor to interpret gaze fixations. Stage 2 is recognition, which integrates and interprets these features. Integration typically happens at feature level, concentrating multimodal features into one vector, or the model level, processing each modality separately and fusing the outputs later. Implicit interaction has been applied across broad areas, that is grounding and communication and state and intent inference. As an example, we introduce enhancing speech recognition, which uses gaze to adapt language model in real time. For example, if you're looking at a specific object, the system boosts the probability of related words, improving ASR accuracy in noisy environment. This even extends to vocabulary acquisition, where gaze fixation helps ground novel out-of-vocabulary terms to visually attended objects. This could be applied to enable state and intent inference. Our review identified 6 key challenges that are temporal alignment, where gaze typically leads speech. Most systems ignore this offset, binding commands to whatever the user fixates on during speech. Limited exploration of fusion strategies. Most studies default to feature-level fusion without comparing alternatives. Annotation and generalizability. Annotation practices are inconsistent, interrelated reliability is rarely reported, and models are validated in narrow-second with limited evidence of cross-user or cross-task robustness. Privacy and ethics. Combined gaze and speech can reveal not just attention, but cognitive state, personality, and identity. Evaluation beyond the lab. Most work is conducted under controlled setting. Real-world settings bring noise, movement, and social dynamics that current systems aren't designed for. Diverse users and context. Very few studies address users with impairment, strong accent, or social constraint on speech. So to wrap up, we contribute a synthesis across 3 decades of research that combine gaze and speech reliably and show that this combination reduces ambiguity, increases expressiveness, and support both precise control and adapted system behavior. We further informed that the real challenge now is no longer whether to combine them, but how to make those combinations robust, scalable, and inclusive.